Okay, so I'm just going to go through a bit more of the details of the PLP. So how we actually do the whole framework. So there's actually a paper on our framework, if you're interested. It was published in JAMA about 2 years ago, design and implementation of the patient prediction framework. So that kind of has some of the details. But there's 3 different parts mainly to the process. So there's the extracting the data and getting the labeled data. There's the training set and test set split, and then you train on the training set and you evaluate on the test set. And we tend to focus a lot on the training and the evaluation, but we don't often talk about how you actually get the labeled data. But this is kind of the key part, really. So even in the paper we published, we didn't really talk too much about the labeled data. So that's what I'm going to dive into a bit more now, just so you can see the process that we actually go through it, because it's quite a unique process that we do to create this labeled data. And I think it's quite different. The shapes obviously changed for the Y screen. So it's supposed to be the whole way. But this is supposed to be highlighting that we're going to be talking about the labeled data. So when we actually look at the data you have in the OMOP Common Data Model, you have people followed over time. So you might have a set point of time, someone comes in, they've got some disease, then later on they have some treatment, and later on they have some outcome. And you have these for lots of different types of illness, like so lots of different conditions, lots of different drugs, lots of different procedures, lots of different measurements. And effectively your data in the CDM looks like for a person ID like 1, you have some sort of concept ID that will tell you this is a condition, this is a drug, this is a condition, and you have the date stamp that they experienced it. So this is the data you currently have for potentially millions of patients. But this doesn't give you any label data right now. So we have to go from this to get the label data. And there's actually been some studies done at the moment where people sometimes will use, there's lots of different designs. So you could do a cohort design, which is what we tend to pick, or you can do a case control design. So some people will kind of center on who has the disease, who never has the disease. Let's look at any time prior. And we're actually doing research to show that a lot of the time you have to make a lot of subjective decisions with a case control design. And it can actually lead to some really bad prediction models that wouldn't probably work when you apply it clinically. So our approach is more of the target, the cohort design you saw, where you specify a target cohort, and then that gives you an index date. You use anything prior to that for the covariates, and you look at some time point after your index to actually do the labeling. So we really stress that you need to define your prediction problem to make sure that you're going to have this labeled data set that is actually going to enable you to develop a model that is clinically useful. And there's a couple of considerations that I think you need to think about. Is it going to be clinically useful? So if I'm doing a model, will it have value? If you're predicting something, say you had a model and you're predicting cancer, for example, and you're predicting someone to have cancer tomorrow. If you had that model, could you really do anything for that patient? Could you do an intervention if they're getting it tomorrow? Does that give you time to do an implementation? Okay. So as I said, so the one key thing is the clinical usefulness. So like when you're doing a prediction, if you were trying to predict something like cancer and you wanted to actually have some intervention, you might want to do your model where you actually start predicting it maybe 6 months down the line. So that if you were to have a model that worked and you could identify the high-risk people, you could do some intervention. So this is one thing I think that needs to be thought of when you're thinking of prediction. I've done a lot of prediction models that aren't clinically useful. So learn from my mistakes and don't waste time on that. And then the next point is the clear time point. So the reason we stress about our target cohort and specifying that index date is because that's going to be the date where you would actually apply your model. That's where it's going to be evaluated at that point in time. So if you have a time point that isn't really well defined that someone's going to be interacting with the healthcare provider, you might have a great model that no one at that point in time is going to be able to actually use it. They're not going to be interacting with their healthcare person. So if you have something like the date that they're given a drug or the date that they're diagnosed, you know they're face-to-face with the clinician at that point in time. So that is a very well-defined point in time for applying the model, and it could actually have value. So these are the 2 key things, I think, for a prediction. And the way we go through that, as you've seen at the beginning, and Peter also went through this, we define everything with the target population, so who it is you want to do the prediction for, and this will tell you the date, the index date that you're actually going to be applying the prediction. Then the outcome, what it is you want to predict, and when you want to predict the outcome occurring. So these are the 3 main components that should actually help you get a good labeled data set. So then how do we get the label data from this? Well, we look at the point in time that someone enters the target cohort. So this could be like the point in time that they have, let's just get the thing. So it could be the point in time they have their treatment. And then we use anything prior to that to construct covariates or features or predictors, however you want to use the term. So all of these records are a free game for constructing covariates. And then we're going to look at some follow-up time. So we're going to imagine, that we didn't have this data. We're going to imagine like this is their cutoff. But we're just going to use this to say, did they have the outcome to get the label? So we do this uniquely by actually defining our target population with logic. Well, that's not unique, but we're going to do the same with the outcome, and that's kind of unique. So we need some logic, which I think many of you would have done the course on Sunday of actually how to do the cohort construction. But generally, it will just be saying, OK, in this place, we want to find people who have 2 or more AFib records, or they have an AFib with an inpatient record, or they have an AFib with an electrocardiogram. So this could be the definition of people who are in our target cohort. And then the index date is the first AFib record satisfying this. So that's the point in time that we're actually going to be indexing on to prior covariates post the time at risk. And this is going to give us a table where we've got lots of different people. You could be repeated. I'm not sure if I put any repeats in here, but sometimes people could be repeated in here. Then you have a cohort definition ID. So at the moment, I'm just showing you one cohort, so this is the same. But if I wanted to, the way the CDM works is you have this cohort table. You can actually have lots of different cohorts in here. So you might have a new cohort that's hypertension people, and that would have maybe a cohort definition ID of 2. So this table can contain lots of different cohorts. And then you have the start date, so when they actually entered the cohort, and then you have the end date. Sometimes you'll have the end date that will be the same as the start date. So in this case, the first AFib date is going to be the same. Sometimes your cohort could be new users of a drug, where your end date might be when they stop the drug. And you can use this for your time at risk as well. So there was an earlier prediction where it was drug users. And I think we were asking you what the end date was for the drug users, and you weren't quite sure of, like, do we want it when people would stop taking the drug? Do we want it at a set time period? You could actually have done the prediction while they're taking the drug, in which case you would have used the cohort end as your end of the time at the risk. Or you could say, OK, I want that 2 months after they end. So you could say cohort end plus 2 months is the end of the time at risk. So you have quite a lot of flexibility with the time at risk. So that's going to be, so this is basically what you do. When you create the cohorts in Atlas, this gets generated in the background. And this is what we're going to be pulling from when we do patient health prediction. And then this is the unique thing. You do the same for the outcome cohort. So when you're defining your outcome, you're going to be defining people again and a date. So it's a set of people that satisfy your logic and a date that they satisfy it. So in this case, we might want to look at ischemic stroke people who have an ER visit. So we've got the ischemic stroke, and we've got that they have to have the ER visit on basically this occurs during the ER visit. So this is the Atlas logic for that. And that again is going to give us another cohort table, but this time our cohort definition is 2. So this is because it's the outcome people. So we have a bunch of people that satisfy it. And we're not restricting our subjects to just the target people at this point, which means that you could reuse this outcome for any target people. If you wanted to look at a different group of people, you could still use this definition that you've defined for your outcome in the future. So we try and make it so you can reuse your target and your outcome cohorts. And then you have your cohort start date and cohort end date, which will get used to basically create the logic for the outcome, whether it occurs during the time at risk. So if you imagine for each person in our target cohort, we actually have all their records. We've got now this index date of when they had the atrial fibrillation. We can use the baseline to create the covariates. And we're now going to look for whether they actually have the outcome, which was stroke, during the time at risk. So if we know they had the stroke here and we know that they had the stroke here, we can actually now say, OK, did they have the stroke during the time at risk? Well, first we need to find out what a time at risk is. So let's get all these across. So if we picked a time at risk of 1, sorry, it seems to make me do this a lot. So we pick a time at risk of 1 day until 130 days. So this is our time at risk here following. We see that it just about fits maybe just before. So I think this person would be a 0 for it. But if we expanded the time at risk till 1 day to 2 years later, What is going on with these slides? So in this case, it definitely fits that they actually have the stroke within the 2 years. So they're definitely going to be labeled as someone who hasn't the stroke during the time at risk. And then if we do with 1 year, we get the same. So that basically means, right. So for each person, we now say, okay, for every person in our database who's in the target population of the AFib, we can create the covariates of things that they have prior to the index. And this will give us, for each person, they have a row. And it says whether they have the conditions or the drugs. Yes means they had it. 1 means they had it. 0 means they didn't. So this is saying, did they have condition A? Imagine this was condition A. They did have it, so it's a 1. Condition B, they haven't. We don't see that up here, so that's a 0. Drug 1, we don't see it in their pass, so that's a 0. So that's how we construct most of our covariates. They're mostly binary. We do have some non-binary, which you'll see later, but the majority are just binary. Did you have it or not? And then we say, okay, did they have stroke during the time at risk, which is this window here represented by the green. And we see here that they did have stroke in this point in time, so their outcome is going to be 1. And so for a time at risk of 1 to 365 years, the outcome is 1. If we'd had a shorter time at risk of like 1 day to 2 days, their actual outcome would have been 0. So we have some flexibility in the label depending on what time at risk you have. But we have this not just for 1, not for just for 2, not for just 3. We have this for many thousands of people often in our data set. So this then gives us a table where we have each row corresponds to a person. So we have the person, we have their index date, and then we know whether they have the outcome during time at risk or not. So we have the label. So this is how we generate the labels with the 2 different cohorts. And then the next bit is to create these covariates, which again, the slides have changed the text a little bit, but I'm going to be talking about this anyway. So with the covariates, we have lots of different ways of constructing covariates. They tend to be linked to the domains of the CDM. So you have a condition table in CDM, you have drugs and device tables, you have procedure tables, and you have measurement tables. So for each of these domains, you can construct covariates. So if you wanted to just look at conditions, you have the option of just saying, I only want conditions. I don't care about these other domains. They're not important to me. If you want to have conditions and drugs, you can do that. You can pick, I just want conditions and drugs. If you want everything, you can say, I want all of these domains. So that's going to be tick options in Atlas. So we have this nice interface where you can just tick, yep, conditions, yep, drugs. And then we also have flexibility of the periods of time that you're looking for where the record occurred. So we have short term, which by default is 1 month prior. So it will be from the index up till, say, 1 month prior. And you're using this part of someone's record to look for whether they have certain drugs and conditions and procedures or measurements. So that's short term. You can change this. So if your short term you wanted to make a bit longer, you can make it to look 60 days back. So there is flexibility on where you actually put this end or this start point for the short term, the medium term, long term, or any term. Actually, any term, you're just looking any time prior, so that's actually fixed. And then the medium term, again, you can, by default, it goes to 6 months back. So it says, okay, if we only look back in the last 6 months of a patient's record, what conditions, drugs, procedures, measurements did they have? And you'll construct features for that. By default, that's 6 months. Again, you can change it. And then long term, by default, is 1 year. So you can say, okay, if we look back 1 year, did they have this condition in the last year? Did they have this drug in the last year? For all conditions and drugs, procedures, measurements. Anytime prior, you don't have to do the subjectivity of saying what time you want to look back. It just looks through the whole history they have. Often patients only have a few years of history, though, in the data set. So a lot of the times, you won't have more than a few years of baseline time for a patient. So you can pick 3 different time periods, and you can also have a hierarchy. So the OMOP CDM has a vocabulary that has a hierarchy. So it says this one code actually has all these children codes. So you could have a general code for diabetes that will then have all the codes that are like specific types of diabetes. So you might have type 1, type 2, and then specific types of type 1, type 2. Things that are caused by type 1 and type 2 might get grouped up to the diabetes concept ID. So with the hierarchy, it will say, did you have this specific concept in the last X number of days, or any of the child codes? So this is kind of nice if you've got, if you've got redundancy in your database, this could be quite nice because rather than having hundreds of covariates that pretty much mean the same thing, you can condense that into one covariate. And then we actually have some records that, or some covariates that are record type count. So how many condition records did you have in the last year? How many measurement records did you have? So this kind of gives you a proxy of healthcare utility. And we also have that for visits as well. So how many inpatient, outpatient visits did you have? Which again, these are kind of proxies for, are you using the healthcare system? We have some common risk scores. So we saw earlier when Peter was presenting, he showed the CHADS score, which was the 5 variables of cardiovascular risk. Or AFib, is it AFib risk? Yeah, AFib risk, I think. So we have that as a score already. So this will be a continuous variable that we have. And we have about 5 different risk scores, and you'll see those in the interface when I go through them later. And the nice thing is that in pretty much all our framework, we've enabled it so you can add whatever you want in. So we actually have the ability to add custom covariates as well. So if you wanted something that's not a standard covariate, you just have to write the SQL that would query the CDM, and then whatever processing you want to do to that, and then you can have your own custom covariate. So some of the cases I've done this for would be someone might say, I want to know if someone's got a measurement between this value in their history, or the actual specific measurement value, or a measurement within a set time. So you can add that in as a custom covariate. We do have some values for measurements, but it uses the last measurement value. So if you actually said, okay, I want to get the H1ABC measurement all time prior, it will actually pick the last measurement that was recorded prior to index. So if you wanted to have it where you looked at some trends of the measurements, you'd at the moment need to do a custom covariate. So we talked about how you can get the labels. We talked about the actual covariates. So now we actually have the complete label data set. So from your T and your O, creating your target and your outcome cohorts, and specifying the time at risk, we can now actually get our label data. But we also have some other options. And these are actually generally done after you've extracted the data. You have then these options of basically looking at sensitivity. So what if I did this? What if I did that? And it means you don't have to extract the data again. You've got your T cohort, you've got your O cohort, and you've got the covariates of people using anything prior to index, or what you specified. Now you can actually say, okay, if I predict the outcome occurring and I don't restrict to first-time occurrence of being in the index, for example, being in T, how does that affect things? If I say they couldn't have had prior outcome versus if they could have had the prior outcome, how does that affect things? And you can do this sensitivity very quickly because you don't have to extract the data again. So if you extract the data once, and then you can try and see, okay, what are these extra settings going to have an impact on the performance? So the first one is, do you want to remove people who have the outcome prior? Sometimes you'll want to do the prediction and say, okay, given that I know someone has never had the outcome, what's their risk of having the outcome? And a lot of the time that will give you a very clean prediction. Other cases you might not care. You might say, okay, having the outcome prior is fine. It's a very common outcome. You're going to have repeats of it. So this is one option you have. And if you say that you want to remove people who have the outcome prior, and you want to look back any time prior, it's going to remove anyone who's, so this is people who've had the prior outcome, they're now going to get removed from your label data. You have this extra option of how far back you want to look. You might just say, I want to look back and just say remove people who had the outcome in the last year. In which case, this person had the outcome more than a year ago, they're actually going to remain in here. But this person is going to be removed because they had it 35 days ago. So you have some flexibility of how far you look back to do this exclusion as well. And then you might want to say, actually, I don't care if people have had the outcome. I don't care if they've had the outcome really close to the index. I'm going to keep them, in which case you'd have everyone in there. And then you've got the option of, do you want to include people in the target population once? So again, do you want unique people in your training data or in your whole label data? So here you've got these two people, or this one person is in here twice. So they entered whatever we define the target cohort in this situation, they entered in 2012 and 2013. But you might want to say, well, if you have them both, maybe that's going to have a bias. If you're looking at all-time prior for your covariates, there's going to be overlap and there's going to be correlation between these because they share a lot of the covariate data. So you might want to just remove one of them. So you could say, should only first exposure per subject be included? Yes. That means that this second time that they entered the target cohort, they're going to be removed. So you've only got one entry per person. So everyone in your label data is unique. If you didn't care about whether they have to be unique, then you can put no here, and this person would enter twice. And then you have, is there a minimum prior observation time? So a lot of the time when we're doing prediction, we want at least a year of prior observation to construct the covariates. If someone entered the database a day before index, you didn't really have much data on them, chances are. So a lot of the time we put a minimum prior observation on just so we actually have data for them. But you might want to see, when you're extracting the data, you might say, okay, I want at least 1 year. But then when you're doing sensitivity, you might think, well, what would happen if I had 3 years of records for patients? Could I have got a better model? So you could actually specify a different look back. So in this case, I've actually made it a 2-year look back. So anyone whose prior observation was less than, so these people were 366, 365, and 588. These were all within 1 year to 2 year that they joined prior to index. They're going to now be removed. So this is a sensitivity that's quite nice. If you have more data, could you get a better model? And then you have the option maybe of actually making it even longer. So I want people to have at least 1,200 days. It's a bit subjective. But if I put that, it would actually get rid of this extra person as well. So we only have 2 people now in this example that have very long prior observation. And then the minimum look back of 365, they all satisfy that, so they would all be kept in. And the final option that you have is, how do you want to deal with people who are lost to follow-up? So a lot of the times, you know that they've satisfied that they're in the database till index, because they're in an index, but they could actually leave the database the next day. So if someone joined on the, say, for example, they joined when they start taking the drug, and then they took the drug to day 60, but then they left the database at day 61. How do you deal with them? Do you keep them in? You haven't really observed them for long. You don't really know what their outcome is going to be. So this is actually a problem that we're trying to look at as a best practice, so I can give you some insight into that. But here's some options of actually how you can deal with it. So say their follow-up is 50 days, 182, 366, 480, 40, and 500. You might have to say, okay, should subjects with time at risk be removed? Yes. So we want them to basically have the whole follow-up. And we're going to say the minimum time at risk is 364 days. So we're trying to, our prediction is a whole year. So in these 2 settings are basically saying we want everyone to at least be observed.
I'm just curious. I mean, so the person you crossed out, that, I mean, even though you only have 40 days of follow-up, you know that they had the outcome. So why would you remove them from your data?
So this is a good question. So that's actually a perfect question for some research I'm doing. So in this case, we're basically saying we want them to have the whole follow-up, but we are also enable you to basically turn that off for people who have the outcome, because you know they've had the outcome. If someone left the database before they had the outcome, you wouldn't know, they're uncertain. But someone who has the outcome, that they can't not have the outcome.
They fit the target that you're trying to...
But when I've actually done research into this, if you look into a year, so if you actually had the situation where you remove non-outcomes who are lost to follow-up, but you keep outcomes, if you make your time at risk very long in the future, say 3 years, what I found is that it causes a bias, because you're not just predicting who has the outcome or not, you're predicting like the survival as well. Right. So then I found that if you do this situation where you keep outcomes, but you don't keep non-outcomes who are lost, and the time at risk is more than 1 year, it actually makes you look like you have a much better model than you do, because your training and your test set all have this bias. So your model looks really good on the training set, it looks good on the test set, but if you applied it to the actual population, it probably wouldn't do very well.
Typically, the way I design my studies is that I make sure that the enrollment criteria is met first, so that they have the minimum pre-period and minimum post-period before I start looking at outcomes. So that way I don't bias myself on these type of decision-making steps.
Well, so what we decided is, what we figured is that if you have a time at risk more than 3 years, more than 1 year, we actually found that just removing everyone, as long as you have enough outcomes, so it would be a problem. If you didn't have much outcomes in the data, it could obviously limit you. But if you have enough outcomes, removing everyone is actually the best choice, because it doesn't bias the data, and you still got enough data to train. If you had a limited number of outcomes, then a survival model would be needed, because then you can account for this loss to follow-up. So we actually have survival models in the PLP package. It's just not linked up to Atlas right now. So you can use survival models if you're doing R code. And we're going to be adding it to Atlas very soon. But right now, Atlas only enables you to do classifiers.
So the minimum time at risk you selected based on your own intuition. Can you program it to be selected based on the best model that can be basically?
Yeah, so the question is about the time at risk. So you're saying it's kind of subjective, but whether it could be programmed to be.
Time at risk, let's say here you selected 1 year of follow-up and you get some model. But if you selected it a year and a half, you would have possibly get a better model. So maybe it's possible to make this as a parameter or something to see what is the best minimum time at risk so you get the best model.
Yes, that's a good question. So you in the framework. So it's about whether time at risk could be modified and parameter. So the time at risk is optional. So you can specify any minimum time at risk, and the way we do it, because you've extracted the data once, and then all the labels get generated after extracting the data because you have all the dates. You don't just have the label, you have the dates. You can actually do a sensitivity to try as many time at risk values as you want and see the impact it has. So that's actually something you can play around with. But from research that I've done, I found that if your prediction is more than a year, you have to be very careful about removing people with the outcome. So generally what I do now is if my time at risk is more than a year, I don't say, I either turn this off and just keep everyone, even though there's going to be noise in some of the labels. Some of the people who don't have the outcome recorded might have had the outcome, but generally it's going to be quite rare. So that's what I probably do, or I remove everyone who's lost a follow-up, which could mean the outcome count goes down, or I do a survival model. So there's kind of 3 different approaches you can do, but there is something but I did find there's a big bias. If you keep outcomes and remove non-outcomes, there is a big bias potentially in the models.
Yeah, I understand, but basically it's kind of a trial and error to find the minimum time at risk, right? You're kind of selecting it by yourself manually, and then you can do some sensitivity analysis around that problem. But I mean, maybe as a future development, you can take a look at something that plays with it as another parameter to the model and see what is the best minimum time at risk for your data that will give you the best model, the best prediction.
I think that it could be quite hard trying to automate the optimal time risk, just because your data you're evaluating on will generally be biased by it. So if you put a large minimum time at risk, it will make your internal validation also have the bias that the data used to develop the model. So it's going to be, I'm not sure how easy. So we only evaluated it by doing simulations. So we simulated if everyone's completely observed, and then we actually simulated removing people, we were able to see the impact of it. But I think with the data, it'd be very difficult to gauge the impact because you don't know whether it's the bias in the data or the model's good. So there's quite a lot of factors. But I think, yeah, if you could have some way of from the simulation, if we could learn some insight to the minimum, that could be really useful. So to follow up the simulation, I think that'd be a really good project. So, and then as I mentioned,
sorry, my question a little more basic. So the index date is closest to T0. So the very first time they have atrial fibrillation will be the index date, and then you're picking up if there are multiple occurrences of the same event going back in time. Is that correct?
So for this one, this is saying whether they're lost to follow-up, there is an option. So if they're, if I go back to one of the plots. So here, for example, if they had the stroke here and here, you have an option of do you want to remove people who've had it prior, and the look back you go, or do you want to? Are you happy with including people like this? So the data will extract everyone. When you extract the data, it extracts everyone in the target cohort, everyone who has the outcome, and every date they have the outcome. You just need to make sure you've defined your cohort to have every date. And then you can use that to filter. So how would the model do if I removed people who had it prior? How would it do if I removed people who had it any time prior versus 30 days prior? How well would it do if I include those people? So you can do the sensitivity analysis of whether to include them. But the data that you extract, or the PLP extracts, it has every date for the stroke. So you can play around with things. So this is actually, so this is the one if you remove everyone basically who doesn't have the time at risk of the whole year. But if you relax this and you said, okay, someone has the outcome, they can be included, then the person this person's actually included still because they're lost to follow-up, but they had the outcome. And like I said, this can cause bias, but then you've also got issues if the outcome's linked to death. You have to do this really. Or you can do a survival model. And then you have the option of, but this person's still removed because they didn't have the outcome. And then you can say, okay, should people with time risk be removed? No. So I'm just going to keep everyone. I know there's going to be some noise. So this person, for example, we only observe them for 50 days follow-up out of the whole 365 days. Maybe from day 51 to 365, they would have had the outcome. So maybe they should be a 1. But the way we've defined it, we're going to have some noise on this label. And maybe that's okay. And this is actually the situation with the simulations we found. Actually, this is actually quite an okay way of doing it. It gives you a more fair performance. So the key thing is to find the prediction problem. You need to make sure that you have defined the target and outcome cohorts in Atlas, or however you want to create the cohort tables. You need to specify the covariates, and you need to specify the population settings. But this can be done after you extract the data, so you could do sensitivity with these. And then the next step is the training of the process. So splitting your data into your training tests and then actually developing the model. So this is the bit where data scientists and stuff will get excited about the work. So the test and train by default, we put 75 into our train, 25 into the test. This is what's default. We also do cross-validation within the training data to find the optimal hyperparameters. So we're using all the training data to develop the model. And then we're validating it on the holdout test set. So the split seed will kind of tell you, it will be used for doing the test and the train and also for the cross-validation. And then you have a split type, so time or person, as Peter mentioned. So I've got 2 columns here to just explain how it does the person and the time split, just as a visual. So if you imagined you had 16 patients, I picked that because it's nice for 25%. And you have the index date for their T. If you're doing the person split, it's just going to simply find 4 of these people randomly to be the test set, and the rest is going to be the train set. So this is just going to ignore this column. It's just going to be randomly assigning 4 people in the patients into the test set. And this will depend on your split seed. And then the time split will actually use this column. So it would actually look at people who have the later data. So this person here was July 2016. This person here was February 2016, February 2014, and March 2012. These are all the people with the latest. So they basically entered the target cohort at a later date. So these are going to be your test, because this is later data, and everyone else is going to be your train because it's the earlier data. So you're going to train on the older data, test on the later data, and this will give you a feel of, does the prediction problem you're looking at solving have temporal changes that could impact? It's not perfect because you might have new temporal things that are introduced later on. So you might find that it does fantastic here, and then 2018 something changed. But it will at least give you some insight as to, like, historically, has it been pretty stable? So then the next part is then training your classifier. So you've got your labeled data, and if you imagine your labeled data in just 2-dimensional space, feature 1, feature 2, and your classes were red and blue. So red may be people who have the outcome, blue people who don't have the outcome. You're just going to be learning a classifier that basically it just tries to find the best decision boundary. So you're just partitioning your space into class 1 and class 2. So people who have the outcome, people who don't have the outcome. So this is all you're doing, really. The covariates that you have, if you have lots of covariates like we have, it's going to be a lot more complex to visualize. The 2 dimensions is nice. Past the 4 dimensions, it's hideous. So we've got a very complex space in general. But the classifier can still try and find that decision boundary. Different classifiers have different decision boundaries. So the tree-based ones will kind of go down and across. They don't really have this nice smoothness as much. So the best classifier always depends on the data because it depends how it's distributed across space. Then you've got your training, so you want to select your machine learning, and then you define these hyperparameters. So hyperparameters effectively control how complex your model is, how complex that decision boundary can be. We have lots of different classifiers built in. So these are the ones that we have in our package. So deep learning isn't in the Atlas interface at the moment. It will be coming in. But all the others are in the Atlas interface. The nice thing, as I said before, you have that custom covariate option. You also have the custom model option. If you weren't happy with these, if you wanted something else, you could actually plug that in quite easily. There's a set of things that need to take, that you need as input into your model, and there's a set thing that you need output. As long as you follow that, you can plug whatever you want in there. We also have ensembles, so you can actually combine lots of these together as well. And the deep learning's expanded quite a lot. We have a lot of different deep learning algorithms outside of Atlas at the moment. So what are hyperparameters? I mentioned that they're basically, they control the complexity, which would affect the decision boundary complexity. So you've got like a simple model. So this is like also, people also say this has high bias, low variance. This isn't going to overfit because it's very simple, but it might not be able to fit well enough to the complex data if you've got complex data. The complex model has high variance, low bias. It's likely to overfit. But if you have data that's kind of all over the place, you might need something that's a bit more complex to be able to separate that out. So this is just a visualization, again, in 2 dimension, because the 2 dimension is nice. I can't visualize more than 2 dimensions, so I stick to this. You've got underfitting, which is here, so where you've got a very simple model. So this is in case you've got a linear model, but your actual decision boundary shouldn't be linear. It should be more of some sort of quadratic. So this is too simple. This is about right. If you had something that was a very high order polynomial, it would be able to perfectly fit and partition on your train set. But it's too complex for this data because these points here, for example, could just be noise. And if that's the case, you're fitting to the noise really well. And then when you've got a new data point, you've pretty got a circle that's here. You're going to be predicting it as red just because your model's too complex and it's just overfit. So it's not going to generalize very well. So you have this like plot which just tells you as the more complex you go, the lower the bias and the higher the variance. So in this area of model complexity, you're likely to overfit. So your train set's going to do fantastic, but your test set's going to be really poorly. So if you are developing a model and you see on the train set you get an error curve of 0.99, and then on the test set is 0.6, you know you're in this situation and you pretty want to make some modifications to make your model a bit more simple. And it could just be that you reduce the number of covariates that you put in when you're doing the design. If you're in this situation where your training and test set are both kind of poor, it might mean that you just don't have good data for the prediction model, or it might be that you need to try some models that are a bit more complex. So we suggest trying lots of different classifiers. There's no one that always wins. The decision boundary that you want all depends on the data that you have, and that's prediction problem specific. We have a lot of classifiers that you can use, so you can just pick any of the ones you want that we have. And we have default hyperparameter grid searches, but you can actually add more if you want to be more thorough. And there's actually going to be some research this year into picking the best default hyperparameter searches so that we can save people some time. So we talked about label data, we talked about training. Let's talk about how you actually evaluate your model and see it's good or not. So we have a Shiny app that gets created. So once you've run your models, you'll get your performance output on the screen as it's running along. And then you can actually view it in an interactive Shiny application. So the main plots for the discrimination, and we mentioned this earlier, we tend to look at the overall. Whether overall is that great when you're thinking in terms of clinical usefulness. It's actually pretty at some point in time, or some point in here that actually is where you'd actually use the model. And we do have that as a dashboard, but for now I'm just going to look at the overall. We have the ROC plot, so this just tells you how well the model discriminates. This actually isn't impacted by class and balance. So the ROC plot, if you predicted everyone as 0, this would actually be on the 0.5 line. It would, on the diagonal, it would be terrible. But what this doesn't tell you is it doesn't tell you how many false positives you get. So if you have a good ROC plot, but your outcome is very rare, say your outcome is 1 in 10,000, and you have an error curve of 0.8, you might think, oh, error curve 0.8, that's really great. Most clinical models have an error curve of around 0.7. 0.8 is fantastic. But if something's very rare, it means that even though you're predicting, you're discriminating well, you're going to have a lot of false positives, which means that your precision is going to be very low still. So the precision recall plot is good for actually seeing, okay, in terms of like the practicalness of the model, do I have a high enough precision? Is my false positive rate low enough? And that's where you might want to look at this plot, which is telling us in this situation, this curve looks good. This is telling us that our precision is less than 10%, which means that we're going to be getting 9 false positives for every true positive that we have. So there's going to be, if you're using that model, if the intervention was horrible, you wouldn't be able to use that because you don't want 9 people to have the intervention for one person that's successful in general. But it depends on the intervention, it depends on the prediction problem. This is why there is no set value that's good. It's really depends on what you're predicting. It depends what you're actually trying to do the intervention for. And it's still subjective. I might be happy with a higher risk of having something horrible if I'm more paranoid about the outcome. Other people might not. So there's a lot of subjectivity when you're applying these. And then we have the calibration plot. So Peter already described this. This is the prediction the model's assigning the actual prediction ground truth. So if the model says I have a 10% risk, will I have a 10% risk? If the model's well calibrated, the 10 points here should fall on the diagonal, which we're generally seeing. So I would trust this model. If this model's giving me an assigned risk, I pretty have that risk. And then we have the demographic plot that is the same as the calibration, but it's per age and gender group. So you can see here whether the model is predicting correctly for the different age and gender groups. In this case, our expected, which is the prediction from the model, and the observed, which is the ground truth, tends to be the same. So we're actually doing pretty well for each age and gender group. We're predicting their risk pretty well. If these deviated, so if the red and the blue line kind of deviated a lot, then it might identify a certain age and gender group that the model's failing for. And then you might not want to use the model for those people. You might want to try and train a specific model for them if you have enough data. So that's the main bits of how we actually construct the data and the theory behind it. After, is it your turn or are you going after lunch? So it's lunch now. So it's lunch now, and then once we come back from lunch, we'll have the tripod work with Ross, and then we actually do the live demo of how to use Atlas.
Yeah, so 45 minutes lunch.
45 minutes. Okay. It's all hands from the cups.